Good afternoon, everyone. My name is Jonathan Hoffman, and I'm a program manager in MTO. I'm very excited to talk to you all today about what I view as an opportunity in quantum technology. But more importantly, I really want to think about planting a seed in your head about how we can approach a number of problem spaces fundamentally differently. And I view this as the initiation of a conversation with these ideas in how we could interact in the future. So, when we are looking at emerging technologies, I want to ask you this question, which is how do we realize scalable and domestic manufacturing capabilities for these emerging technologies? In MTO, we build some of the most exquisite devices in either quantum technologies, quantum sensing, integrated photonics, organic circuits, or even unconventional computing. But then, and when we do that, our goal is to take disbelief to doubt. And as Whitney mentioned earlier, unfortunately, after we do this proof of concept, it's 15 years until that hits our market. And this is an unreasonable economic gap and national security risk. So I want you to think about how, for these emerging technologies, we can approach that problem differently. And to approach that, I would like to know what the actual figures of merit would be to realize scalable domestic manufacturing. What are the economic structures and frameworks that we need to actually realize in order to translate these proof of concept demonstrations into commercial products? And are they actually different than our historical technologies we've built? Is there something fundamentally different about a quantum sensor or integrated photonics? And when we actually understand that challenge, when we know what that figure of merit is, MTO can do what MTO does best. We can make exquisite devices that are both manufacturable, but also develop the tools to realize the scalable manufacturing all at once. And so I want your help in answering this question. Now, more specifically in a space that I'm personally a lot more comfortable with, in quantum sensing, let's look through this through the lens of how we can manufacture and proliferate quantum sensing. So on this chart, pictured is a plot. If we look at the plot, on the left hand, the y-axis is the relative performance versus the x-axis, which is a manufacturable figure of merit. You should question my manufacturability figure of merit. I've made a choice that it is the number of parallel devices made divided by labor hours divided by human touch points. That is something that you should question. And what we find in our top left corner here is the most exquisite sensors ever built. My normal shtick is quantum sensors have taken the most precise measurement of electric field, magnetic field, frequency, time, acceleration, rotation, and gravity. But it's not really a household product. They don't really exist at scale that everyone is using and purchasing. On the bottom right corner here, you have scalable electro-optics or electronics that might appear in your phones. And what we want with all good DARPA things is to go up and to the right in this white space chart. But where we typically stand is this central region, which are excellent sensors, but typically you could think of as bespoke Swiss watches. So the question I want to pose is, how do we get out of that thought process? Before I get into that, I want to tell a slightly different story. So we pitched a program recently called the Robust Quantum Sensors Program. And I went through my normal shtick. I said quantum sensors have produced the most exquisite measurements of time, field, frequency, blah, 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 blah. And then posed the question, why are they not deployed everywhere? And when we went back and reflected on this, we said, well, the way we design quantum sensors is possibly wrong. Historically, we've made them to be as sensitive as humanly possible. But when we do that, we don't think about what makes them not function on a platform. So we have a bunch of interferers from the platform itself, stray fields, stray field gradients, and vibrations, which ruins the promise of quantum sensors when you put them out there. And so we said, is it possible to actually build a quantum sensor from the ground up that is both sensitive and immune to these platform disruptors? If we do that, and we look at the technology readiness level chain, we can actually collapse it. So I say all of this to draw an analogy. Typically, when we build a device, we think, I'm going to move down tier 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe, and then I'm going to start worrying about the manufacturing readiness level chain. 1, 2, blah, 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 down. Is there a way of fundamentally rethinking how we build our sensors that we merge the MRL and TRL together and collapse both of these chains in a way that gives you a useful quantum sensor and one that is scalable and manufacturable? I believe this is possible, but I believe we have to build a number of technologies to make this happen. So from that perspective, I want to show what's going on the outside of this chart. So what we're pictured in the top left is reduction in size of atomic housing. On the bottom left is great wafer scale manufacturing of vapor cells. On the bottom right is an ultra-high vacuum chamber. And on the top right is great routing of integrated photonics. And what I'm positing here, which I would love to get all of your input on, is that what we've done is built individual elements, housing, light, electronics, of a full quantum sensor stack. And what we need to do is take your favorite qubit, whatever that is, if it's an atom, an ion, a spin qubit, a defect in some other solid or a special material, and I need to bring in my electronics and my photonics together and route at all of these seams to realize my control, manipulation, and readout of my sensor. And today, we don't have that seamless integration. So this is one of the things I really would like your help on, figuring out how we can realize this to tackle these challenges of integration and parallelization of heterogeneous and homogeneous quantum sensor systems. Before I move on to the next slide, we're going to switch topics a little bit into something a little more specific. So here, I'm interested in better understanding how we can revolutionize RF receive. I'll talk specifically through high frequency sensing. So high frequency, or HF, covers the 3 to 30 megahertz band. This has had a renewed interest for over-the-horizon radar and various communication schemes. And to get a sense of scale here, a 3 megahertz frequency translates to about 100-meter wavelength. So if I want to build a lambda over 2 dipole, that means I need 50 meters of dipole to actually realize that. That'll be a great sensor, but it's not really practical to take into the field with you and travel around with. So what we were interested in figuring out is it possible to do this in a 1 centimeter, 2 centimeter device? And now I'll tell the story through the Quantum Apertures program. Pictured on the left here is a plot of electric field sensitivity on the y-axis, down is better, versus the frequency that you might want to receive on the x-axis. Typically, if you're above 1 gigahertz or so, it's very easy to have something that's not electrically small. When you get below a gigahertz, 100 megahertz and lower, you'd be what's called an electrically small antenna. If we look at this chart, the dark gray is a low noise environment, the light gray is a high noise environment. Typically, you want your sensors to operate a little bit below that low noise environment. And what we found in quantum apertures is this blue line here. And that's not just quantum apertures. This is a literature search on all Rydberg receivers and antennas that are out in the field. And we can be comparable to a lambda over 2 at about 10 gigahertz or so, but our sensitivity severely degrades as we go to lower frequencies, to the point that we're no better than a 1 centimeter dipole, and we've got a 4 order of magnitude gap in our performance versus the low noise or the high noise environment. This is not acceptable for all of these applications. So the question I want to pose to you is, how do we change our quantum sensing and revolutionize sensing in this frequency band to get centimeter scale dimensions? I think there's opportunities in new sensing modalities. I am interested in seeing if there's a way to change the way fundamentally we receive RF with Rydbergs. I'm a little skeptical right now. I don't see a solution there, but I'm very open to ideas. And finally, I think there's opportunities in quantum and photonic backend processing that can turn other antennas into very, very precise receivers, giving up the sensitivity of the antenna by gaining on the back end. So this is something I really am interested in your feedback on. The next topic is a little more speculative. And the idea would be, is it possible to create high permeability and high permittivity materials with incredibly low loss? Industry has used high permittivity and high permeability materials for capacitors and transformers all over the world. But I think it would be really interesting if we could design these properly to have the right ratio of epsilon and mu to turn an electrically small antenna into an electrically large antenna just by these material properties. I will tell you, I'm not convinced these materials exist. If they do, please tell me, but I have not seen enough evidence that that's real. So to me, that means, what are the tools we need to build to simulate and model how we can create these materials? And then once we understand that, how do we create and fabricate them into usable designs? And so I'm very interested in your feedback on this. Now I'd like to end by thanking you for your time and saying we need your help. Everything we do at DARPA is not possible without you helping us build these visions and executing that mission. I'll be here for the next 2 days, and I'm happy to sit down and chat on any of these topics and more, but I really need your help specifically on how we realize scalable domestic quantum manufacturing. And with that, I want to thank you all for your time.